Hello and welcome to Empowered Learning. This particular video will be on solving rational equations. If you have not checked out my videos on properties of rational expressions and functions, there's two parts to that. I would recommend that you check those out if you are just starting to now deal with rational equations and or rational expressions to sort of get an idea of the kind of things that you need to know and have in your toolbox to be able to do this particular skill, which is solving rational equations. So we're going to first talk about what an actual rational equation is, some of the vocabulary and things that we need to know about rational equations, and then we will solve a few. The method that I'm going to use to solve these rational equations will be the method of multiplying the LCD by both sides of the equations to get rid of anything that looks like a fraction. Okay, and so we're doing that to simplify the process. So let's go ahead and get started. So the first thing that we know here is that whenever we're talking about equations, a rational equation would just be a rational expression on at least one side of an equation. So let's say if we have something like this. So x divided by x plus 1 minus 2 equals 4x divided by x plus 2. So something like that would be a rational equation. So here we can say a rational equation is an equation that contains at least one rational expression in it. A rational expression is an expression that looks like a fraction where its numerator and denominator are polynomial expressions or numbers where the denominator is not allowed to equal 0. Okay, so in my earlier videos, I basically nickname rational equations as polynomial fractions because that's really what they are. So, of course, a rational equation just has polynomial fractions on at least one side of that particular equation. Now, there are two primary ways to go about solving a rational equation. One way, which is called find the least common denominator of all the rational expressions, and then you multiply both sides of the equation by the LCD in order to get rid of the polynomial fractions. This will be the method that I'll be using in this video. Okay. There is another method where we still find the least common denominator. Okay. But at this point, instead of multiplying both sides of the equation by the LCD, what we do in this case is we find equivalent rational expressions. And then after we do that, we know that once that's done, we know that the denominators are going to be the same for all of the expressions. And so because of that, we go ahead and equate each side of the equation, in particular the numerators for each side of the equation, because we know if the denominators are equal, then that means that the numerators would have to be equal as well. And that essentially gives us the same thing. However, it's a little bit more involved. So if you look at the previous two videos that I've made on this particular topic of rational expressions and functions, you'll see that it does take a little bit more to actually get those particular equivalent polynomial fractions before you start doing anything else with them. Okay. All right, so let's talk about this concept of an extraneous solution. Okay, and I'm going to start off here by basically giving you a nice linear equation to explain the concept. Okay, so we know that sometimes when we have linear equations, and let's say we have this one, let's say we have 2x minus 1 equals 2x plus 2. Okay, And so in this particular case, if we were trying to solve this equation, we would see that we would get no solution, okay? Easily being because if we looked at the graph of 2x minus 1 and 2x plus 2 graphically, we would see that both of those lines are parallel to one another. Hence, they do not cross. If we went ahead and did this algebraically, we would see that this would equal to -1, and that would be 2. And of course, -1 is definitely not equal to 2. So this tells us that we have no solution. Okay. Now, a rational equation is different in that sometimes we get this particular scenario here where we know that there's no value of x that would actually work for the equation. But the thing that's different about rational equations is that sometimes when we solve a rational equation, we will get an actual answer for it via the process that we're about to do. And if we go back and try to plug in or substitute that particular number or numbers back into the rational equation to see does it actually work, in other words, checking your solution, we'll find out that it won't work, okay? The good thing about rational equations is that the way that they're structured, it makes it very easy to figure out what values of x will work and what values of x won't work. And we can actually figure that out before we actually get started. So we don't have to go through the tedious process of solving the rational equation and then afterwards plugging it in, because we already know what we can't have to begin with, okay? And this is essentially what we do whenever we find the domain of a rational function, a rational expression. So if we know what values of x we can't plug into those expressions, then we also know what answers we can't have for a solution to a rational equation, okay? And so that's pretty much what we're going to talk about next here. So it says, since some rational expressions are able to be evaluated for all real numbers that are in the domain of a corresponding function, it is easy to know what values of x can't be solutions for a rational equation, okay? And so we've already talked about that. And so if we move down to the second paragraph, it says, when using method 1 or method 2 that was mentioned, in other words, using the LCD to multiply both sides of the rational equation, method 1 or method 2, using the LCD to form equivalent polynomial fractions, aka rational expressions, and then equating the numerators together. If we have a situation where the process gives us an answer or a value of x that makes the denominator 0, then this is what we call an extraneous solution, okay? And that's just fancy for a solution that doesn't work, okay? And so we discard any of those types of solutions after we've done the whole process of solving the rational equation, okay? And so one suggestion that I have here is that anytime we have these rational expressions, it's suggested that you try to factor out the expressions that you have as much as you can so that you can clearly see what values of x make your denominators for your rational expressions in your rational equations equal to 0. And so that way we can know, we can begin with the end in mind in trying to know what we can have a solution and what we can't, okay? All right, so let's go on to the first example. So for this first example, we notice that we have an x in the denominator for the rational expression that is on the right, okay? So before we even get started, we know that x will not be able to equal 0. So if this process yields us x is equal to 0, then we know we have to throw that out as one of the possible solutions, okay? Now, again, I do realize that for this particular example, that we can do this in two different ways. The way that I'm going to do it first is I'm going to use our LCD and multiply both sides by the LCD to get the answer. I will do this another way just to show you that if we're fluent in adding and subtracting fractions, that there is another way to do this. But I want to showcase the method one of using the LCD and multiplying both sides of the equation by that first. Okay, so if we look at our denominators, we have 3, 4, and x. And so the LCD for all three of these denominators would just be 12x. And so the reason for that is, again, if we do the process of finding an LCM, we have 3, we have 4, and we have x. X is a prime, so we can just break it down as x. 3 is a prime, so we can just break that down as x. 4 is composite, but is broken down to 2 times 2. And so we know if we have 2s, 3s, and x's for our distinct prime factors. And so we just circle the most amount of 2s in a row, most amount of 3s, most amount of x's. And as you see, we've pretty much circled everything. So that is why we have an LCD of 12x here. So in doing that, we need to multiply both sides of our equation by 12x. Okay. So on the left side, when we do the distributing, we have 12x times 4, all that divided by 3, plus we have 12x, all that divided by 4, and on the right side, we just have 12x divided by x. And so here we see that 3 and 12 both have a common factor of 3. So 3 goes into 3 once, 3 goes into 12 4 times. And I didn't want to connect it like that. So let's change that 4 times. Okay. And so now what that leaves us with our first term is 4 times x times 4, which is 16x. Plus, we know that 4 and 12 have a common factor of 4. So 4 goes into 4 once, 4 goes into 12 3 times, and now we just have 3x that's left there. And of course, these x's here reduce to 1. And so we just have 12. So now you see that we've essentially rid ourselves of these polynomial fractions, and now we have just a nice linear equation left. And so if we combine like terms, we know that 16x and 3x, 19x, that equals 12. And then we just divide both sides by 19. And we see that our answer is 12/19. Now, notice that 12/19 is not the same thing as 0. So therefore, we can actually keep this solution, and it is valid. And because of this, we do not have to go through the process of plugging in 12/19 back into this particular equation and to see whether it actually works or not. We know that it does. Okay. So that is this particular example. I'm going to now erase this and work this another way, just so that we can see that we don't always have to use this particular process to do it, especially being that we just have these numbers here. But, you know, again, it's just another way to do it. So we'll go ahead and continue now. So the other way that we can do this is we can actually form an equivalent fraction here. And so we know that, again, that our LCD is going to be equal to 12, and that's just if we're considering these two denominators here. And that means that for this first fraction, we need to multiply both numerator and denominator by 4. For the second fraction, multiply the numerator and denominator by 3. If we do that, the equivalent fraction ends up being 16 over 12 plus 3 over 12 equals 1 over x. Now that we have like terms, we can add the fractions, and now you see that 19 over 12 is equal to 1 over x. Well, 1 over x is just the reciprocal of x, so if we solve for x, then that means that we have to take the reciprocal of our fraction 19 twelfths, which is 12 19ths. So again, this is another way that we can do this particular problem. It is more simple to do it this way for this one, since we just have these fractions on the left side here, okay? But the technique that I had shown in the first example is what is important, and we're going to be using that again, okay? One other way that we could do this is that we can also do this cross multiplication thing, where we just say 4 times 4, which is 16, plus 3 times 1, which is 3, all over 3 times 4, which is 12. So we can also do it this way. And then we see that we end up getting 19 over 12. And of course, x is now 12 over 19. So we have all these different ways as well. Okay. So moving on to our second example. Here, this is something a little more like what we would normally see whenever we have a rational type of equation. And again, I will solve this two different ways. The first way that we're going to do this is by the LCD again. But before we do that, we need to know what values of x we can't have for our solution. So we know that our denominators are not allowed to be equal to 0. Okay? So if we solve that, we'll see that for the first particular case, we know that x will not be allowed to be equal to 3/2. And for the second case here, we know x will not be allowed to equal -5. So we know what our two values of x are that is not allowed. Okay. Now, the easier way to do this particular example is to do a quick and dirty method, which we call cross multiplication. Okay, we're going to do this method first and then do the traditional LCD multiplying on both sides method, so you see how that works as well. Okay, so if we cross multiply here, we'll have 3 times x plus 5 equals 2 times 2x minus 3. Okay, and then we just distribute. We'll have 3x plus 15 equals 4x minus 6. And then from there, we just solve for x. So I'll subtract 3x from both sides, and I'll add 6 to both sides. Okay, and so that cancels to 0. 15 plus 6 is 21. 4 minus 3x, well, 4x minus 3x is just 1x, and that cancels to 0. So we see our answer is just x is equal to 21. And of course, 21 does not match -5 or 3/2, so we are good to go. Okay, so that's one way that we could do this particular example here. The other way that we can do it is by multiplying the LCD by both sides of the equation. Okay, and so we're going to go ahead and do that now. So I'll go ahead and erase all this business. All right, so if we do it the other way, then we know that our LCD here is just going to be 2x minus 3 times x plus 5, because both of these denominators are prime expressions, meaning that the only thing that we can break these expressions down to into factors is just 1 in itself. Okay, so we'll take 2x minus 3 times x plus 5, and we will multiply it on both sides of our equation. Now, when we do it this way, you'll see that on the left side here, we kind of see that the 2x minus 3 and 2x minus 3 are common factors, okay? Since they're common factors, because meaning we can put this over 1 and kind of bring all that together. So this and that will reduce to 1, and we just write what's left, which will be 3 times x plus 5. And then on the right side, the same thing. We can put this over 1, and we see that we have, x plus 5 being a common factor, and that reduces to 1. And so on the right side here, we just have 2 times 2x minus 3. And then, of course, it looks the exact same at this point. Okay. So here, subtract 3x from both sides, add 6 to both sides, and we see that x is equal to 21. So same kind of thing. Okay. All right, let's move on to the next example. Okay. So for this type of example, again, there's a couple different ways we could do it. I'm just going to start off by identifying that the LCD here is just going to be x minus 2, and that we know that x minus 2 is not allowed to equal 0, which means x can't equal 2. Okay, so we start here, we multiply both sides of our equation here by x minus 2. Then if we distribute, we'll see that we have x times x minus 2 over x minus 2 plus 3 times x minus 2, and that will equal 2 times x minus 2 over x minus 2. And of course, that reduces to 1. We'll distribute here, and these factors reduce to 1 as well. And you see we have a nice simple linear equation at this point. So x plus 3x is 4x. And then we can just add 6 to both sides. And so finally divide by 4, and we see that x is equal to 2. Okay. However, we see that 2 matches this right here. So in this case, we cannot use this actual solution here. And since that was the only solution that we had, then the solution that we're actually going to have is no solution, in which we denote by the null set. Okay, so we can just say no solution here. So this is a case where we have a rational equation that's set up, but there is really no solution to it. Okay, and basically what this means is as follows, and I'm going to erase a lot of this stuff so that I'll explain what's going on here. Okay, so what's actually going on is the following. Okay, when we say we have this equation here and this equation here, we could look at this as a graph of a function, and we could look at this as a graph of a function as well. And of course, just like with lines, remember this example here that I gave you in the beginning, this line kind of looks like this, and this other line here looks like that. Let me redraw that because that wasn't correct. So it kind of looks more like this, where both of these lines have the same slope. They're parallel to one another. Okay, and so these two lines will never cross, so there's no solution to it. Similarly, in this case, we have two functions that, for whatever reason, because of how they are actually made, they will never cross each other. Okay, and so the only place where you think they would actually cross is when x is equal to 2. And for those of you that have studied rational functions in particular and know about the concept of a vertical asymptote, you'll know that the only place where these functions cross is at their vertical asymptote. Okay, and of course, vertical asymptote is a x value that is undefined for these particular functions. So again, that's why we have no solution for this particular equation here, because they do not cross anywhere at points that are defined on each of the graphs. Okay. All right, so let's go ahead and move on to the next example. So for this example, this is a case where we want to try to factor out what we can here. Okay, so we see that x squared plus 3x minus 10. If we're looking at this, so have x squared plus 3x minus 10. If we factor that out, we're suspecting that it's just going to be x minus 2 times x plus 5, but we just want to be sure. And so here we know that the factors of 10 that have a difference of 3 are indeed 5 and 2. And so if we let 5 be positive, 2 be negative, then that would work. Okay. So here we are going to be replacing this with x plus 5 times x minus 2. And so what this tells us is that since we know that x plus 5 times x minus 2 cannot equal 0, oh, excuse me, didn't mean to phrase it that way. We know that x plus 5 cannot equal 0 and x minus 2 cannot equal 0 because of what we see here and here. But that also applies for this part too. So this tells us that x can't be negative 5, and this tells us that x cannot be equal to 2. So as long as we do our process here and we do not get negative 5 or 2 as a solution, then we're good. Okay. All right, so moving on, we're going to take our equation here and multiply both sides by the LCD. And our LCD in this case is just going to be x plus 5 times x minus 2. Okay. So if we go ahead and do that, this is what this looks like. We'll have x plus 5 times x minus 2 due to the left, and then 3 over x plus 5 plus 10 times x plus 5 x minus 2. And I'll go ahead and get rid of some of this stuff here so we can have some more room. We want to keep that. Okay. So x plus 5, x minus 2. That way, just keep that separated. All right. Let's try this standpoint. Yeah. All right. So now that we have that, let's go ahead and combine everything together. So here we can put this over 1, and we see that we have common factors of x minus 2. And then that just simplifies to 2 times x plus 5 on the left. On the right hand side, we will have to distribute. So I'm going to write this out so that we can clearly see what's going on. So our first term looks like this, and our second term will look like this. Okay. Now, from here we see for the first term on the right side, we have common factors of x plus 5. So those reduce to 1. And we just have 3 times x minus 2. plus, we see that we got common factors everywhere here, and all we have left is 10. And so we can go ahead and distribute here. And so now we have a nice linear equation. We'll go ahead and distribute 3 to both of these terms. Bring this down. So now from that point, we can go ahead and finish up. And so here we know that we can subtract 2x from both sides, and we can cancel here. That'll just be x minus 6 plus 10. Minus 6 plus 10 is a positive 4. And so then from there, we can just subtract 4 from both sides. Okay. And when we do that, we know that that cancels. We get 6 on the left, x on the right. And so x equals 6 is our answer. And if we look back up here, we know that the answers that we could not have were -5 and 2. And of course, 6 does not match that. So therefore, 6 is the solution. And so conceptually, what this means is, if we looked at a graph of 2 over x minus 2 and a graph of all of this, the one place where both of these graphs will actually intersect one another will be at the location where x is equal to 6. Okay? And that will be the only place where these graphs would intersect. And with that, that concludes this particular video of solving rational equations by using the least common denominator, or the LCD, to clear out our polynomial fractions plus some other methods. Thank you for checking this out.